Hi, in this video we will discuss Gauss quadratures. Now, for Newton-Cotes quadratures, we already know that the integration points are given by the problem. They are typically, but not always, equispaced points. Okay, if the integration points are given, this means that we have n plus 1 degrees of freedom, that is, the integration weights, in the design of the quadrature. And with these n plus 1 degrees of freedom, we can devise quadratures of order n. That is, quadratures that integrate exactly polynomials of degree n, polynomials with n plus 1 coefficients. The idea of Gauss quadratures, on the other hand, is the following. Can we choose optimal integration points in order to have a higher order quadrature? More specifically, if both integration weights and integration points are degrees of freedom in the design of the quadrature, so we have 2n plus 2 degrees of freedom, is it possible to get order 2n plus 1? Let's explore this. What we do is simply to choose the integration points z and the integration weights w so as to integrate exactly monomials p equal 1, p equal z, p equal z squared, dots up to p equal z to the power of 2n plus 1. Okay? And this leads to a nonlinear system of equations with 2n plus 2 unknowns and 2n plus 2 equation. If we achieve this, then the quadrature has order 2n plus 1, and the integration error can be expressed like this, where we note here the derivative of order 2n plus 2 of function f. Let's see how this works for a quadrature with n equal 0, that is 1 integration point, and n equal 1, 2 integration points. Okay? So for n equal 0, we are going to require the quadrature to integrate exactly these two monomials and derive the corresponding point and weight. For n equal 1, we will impose the exact integration of these monomials to obtain 2 points and 2 weights. So let's go. For n equal 0, we need integration point z0 and integration weight w0. So for pz equal 1, the analytical integral is 2, and this has to be equal to w p evaluated at z0, that is w0. For pz equals z, the analytical integral is 0, and this is equal to w0 z0. So from these two equations, we obtain z0 equals 0 and w0 equal to. In other words, the Gauss quadrature with 1 point uses the midpoint of interval minus 1, 1 and an integration weight that is equal to the length of the interval. Okay? This is for n equal 0. For n equal 1, we are looking for points z0 and z1, weights w0 and w1. So we'll require the exact integration of these monomials. For pz equal 1, this is 2, equal to the sum of the weights. For monomial z, this is 0, equal to w0 z0 plus w1 z1. For pz equal z squared, this integral, this analytical integral is 2/3. This is w0 c0 squared plus w1 c1 squared. And finally, for z cubed, this integral is again 0 and equal to w0 z0 cubed plus w1 c1 cubed. Okay? So we have here in a linear system 4 equations, 4 unknowns, okay? And because of the symmetry pattern in this system, we start looking for a solution with w0 equal to w1 and z0 equal to minus z1. With this extra information, we can easily obtain that the two weights are equal to 1, z0 is minus square root of 3 over 3, z1 is square root of 3 over 3. In other words, the Gauss quadrature with 2 points uses these very special integration points z1, z0, okay, this is roughly 0.57, with integration weights equal to 1. In fact, there are different families of Gauss quadratures. So we call them Gauss-Legendre quadratures in case we are integrating polynomial f from -1 to 1. Okay? We can think that inside the integrand we have a weight function w z equal 1. We call them Gauss-Legendre quadratures in case we go from 0 to infinity and f goes together with this exponential. Gauss-Hermite refers to this integral from minus infinity to infinity together with this weight exponential of minus z squared. And finally, Gauss-Chebyshev in case we go from -1 to 1, so again a finite interval, together with this weight. Okay. For all these families of Gauss quadratures, integration points and weights are well known and are tabulated either in paper or electronically. Now, for the most widely used Gauss quadratures, okay, the ones that go with weight 1, here we have the quadrature with one integration point that we just obtained, same with n equal 1. N equal 1 means we have 4 degrees of freedom, 2 weights, 2 integration points, so this is why we achieve order 3. And by a similar approach, we can derive the quadrature for n equal 2, 3 points and 3 weights of order 5. Okay. Please note the symmetry in the points. Okay, so we have Z1, 0 and Z0, Z2 are opposed. And also the symmetry in the weights with W0 equal to W2. These are the kind of tabulated values we referred to. So if we zoom in, we can see here the quadrature for n equal 0, n equal 1, and n equal 2 of the previous slide, and also higher order Gauss quadratures for n equal 3, n equal 4, n equal 5, and so on. An example on how to use Gauss-Legendre quadrature in the general case where the interval of integration is a, b, rather than -1, 1. Okay. Well, this is very simple. All we have to do is a change of variables. Okay, so this z goes from -1 to 1, and this x goes from a to b. Okay. b minus a over 2 is simply the Jacobian of this change of variable. Okay. Now, with this change of variable, the integral can be expressed simply as b minus a2 of an integral that is already in -1, 1. Okay. With small f defined as big F for this auxiliary variable. If we simply apply a Gauss-Legendre quadrature to this integral, we do a summation of integration weights times f evaluated at integration points. Okay. And we obtain finally this expression where the truncation error has the derivative of order 2n plus 2, thus showing that the quadrature is of order 2n plus 1.